this is the work that, we've done that really focuses on how the spatial nanotopography influences, cell behavior. And this is, really based on, the work that we've done in our lab over a number of years, showing that vascular cells respond to nanoscale patterning cues at the order of like tens to hundreds of nanometers. And, in this work, we focused on how these anisotropic or parallel aligned spatially nanopattern scaffolds can be used to create vasculature that is spatially oriented. And this is very much the case in cardiac muscle and skeletal muscle, just to name a few, applications. And so for us, this is something that is very important for creating engineered tissues that mimic their physiological structure. And we tend to think of the vasculature in these tissues like heart and muscle to be like muscle that are interspersed with parallel line vasculature. And so we use a very facile approach to create extruded collagen scaffolds that are very long and thin with dimensions very similar to that of like suture materials. So long and thin that have diameters maybe of about 300 microns in thickness. And when we extrude them, we can also bundle them up to create, bundles of scaffolds to mimic the bundled-like skeletal muscle structure. And so in these studies, we essentially looked at how these bundled-like spatially patterned scaffolds can be used to create organized vascular regeneration in the skeletal muscle system. And in these studies, we cultured endothelial cells in conjunction with skeletal muscle myoblasts, which are the cells that give rise to new muscle fibers. And we looked at the effects of these spatially patterned scaffolds either in co-culture, so with both cell types, or just in the absence of the endothelial cells, so meaning only having, the myoblasts, to see what is the added benefit of having the addition of endothelial cells. And furthermore, in terms of the organization of the vasculature, we also compare these anisotropic spatially patterned scaffolds as well as ones where they don't have this kind of organization. So this is our conventional scaffolds, which we call, randomly oriented, because in typical scaffolds, the collagen fibrils will be organized in more of a disorganized random appearance. And when what we basically found is that these spatially patterned scaffolds are very important both for signaling as well as for regeneration. So when we culture both endothelial cells with these skeletal myoblasts, it's just simply in vitro, we can see that the endothelial cells, their presence actually help to create longer looking myotubes, which are precursor skeletal muscle fibers in vitro. And when we look a little bit more deeper at their underlying biology, we find that their proteomics are very different when they are on co-culture on these aligned scaffolds compared to if they're just growing on randomly oriented scaffolds. And in particular, on these spatially patterned scaffolds, the endothelial cells are capable of producing a lot more pro-angiogenic growth factors, and which we thought was really surprising and interesting to show that the endothelial cells can actually have different kinds of protein secretions based on the kind of topography of scaffold they're on. But more importantly, when we implanted these scaffolds that either have this aligned or randomly oriented scaffold structure, in the presence of either just the monocultured myoblasts or in co-culture with endothelial cells, what was most striking was to find that on the aligned scaffolds in general, we were able to create much more organized vasculature in the mouse muscle. And not only that, we were also able to get improved muscle regeneration as well. And this was done histologically based on staining of skeletal muscle myosin heavy chain. So, and in the end, we were able to better recapitulate the physiologically oriented structure of skeletal muscle in terms of being able to regenerate oriented skeletal myofibers in vivo that are interspersed in parallel with spatially aligned microvasculature. So this work has important implications in how we can create more physiologically relevant tissues using spatially patterned scaffolds, as well as just more broadly speaking, how to be able to induce or create vascularized engineered tissues for in vivo testing.